All right, this video will go into more detail with the graphing irrational functions, and we'll include both slanted asymptotes and holes in this video. If you need additional help, make sure you watch the other videos that are posted under the Math 3 side on the EC Wildcat Math. All right, here we go. For these, we're going to find all the intercepts and asymptotes. We're going to find the domain of the function and determine if it's continuous. And lastly, we're going to sketch. So let's look at a function. Here we have f of x equals x squared minus 7x plus 12 divided by the quantity x squared minus 9. Recall from previous discussions that the numerator or the top gives me the solutions that are going to become x-intercepts if they're real. And the bottom, if they're real, are going to be where the vertical asymptotes are. All right, so let's start by factoring out this function. If we factor it out, we get f of x equals the quantity x minus 4 times the quantity x minus 3 divided by the quantity x plus 3 times the quantity x minus 3. Now looking at this, you may be inclined to think that there's two x-intercepts and two vertical asymptotes. But notice something real quick. X minus 3 is a factor of both the numerator and the denominator. Negative 3 can't be both an x-intercept and a vertical asymptote. It can't be a point on the graph being an x-intercept and a point where the graph is undefined being a vertical asymptote. That doesn't make sense. So what is it then? This is what we call a hole. It's a removable discontinuity. It's a little single point that the graph does not exist at. So what we'll do instead is we're going to cancel out those common factors. We can cancel out the factor x minus 3 on top and x minus 3 on the bottom. But because of the original function, x could not be 3. So when we rewrite this, we need to say it's the new function f of x equals the quantity x minus 4 over quantity x plus 3. But keeping in mind, x cannot be 3. We need that little exclusion written down so we know that 3 is not part of the domain. All right, let's take a look at this new function and figure out these pieces that we're asked to find. Let's start with the intercepts. We know from the numerator that that's where I'm going to find my x-intercepts if the solution's real. Well, here, x minus 4 equals 0. X is 4. That's the x-intercept, 4, 0. To find the y-intercept, we'll plug f of 0 in and see what we get. Into this new function, 0 minus 4 over 0 plus 3 becomes negative 4/3. The y-intercept is 0, negative 4/3. Now, you could have also done f of 0 with the original function, and you would still get negative 4/3, but it's going to be a little bit more work. All right, now we said that there's going to be a hole when x is 3. Let's see if we can figure out where that hole actually is. I know the x value, but what's the y value? Where is this hole going to be? To do this, I'm going to take the new function, and I'm going to substitute 3 in. Now, I'm using the notation y equals 3. It's really not a good idea to use function notation when something is outside of the domain. I really don't want to say f of 3 if I'm saying 3 is not in the domain. So I'll say y equals instead. And up top, 3 minus 4 is negative 1. On the denominator, 3 plus 3 is 6. And I'm going to get negative 1/6. And what this is telling me is that the graph breaks, or there's a hole, at 3, negative 1/6. It's a single point that's removed from the graph. Now, if I tried using the original function instead, the x squared minus 7x plus 12 over x squared minus 9, I tried plugging in 3, and let me show you what happens if you try using the original. If you plug it into the original function, 3 squared is 9, minus 7 times 3, which is 21, plus 12 over 9 minus 9, this is going to give me 0 over 0. And that's called an indeterminate form. 0 over 0 doesn't work, and we really can't tell what it is. Is it supposed to be a 0 value? Is it supposed to be undefined? Instead, it's indeterminate. This kind of warns me that, you know what, there's a simplified version that I need to use instead. So, long story short, when you're finding where the hole is, don't use the original function. Always use that new simplified equation instead. This will actually tell you where the hole is. I can actually see it's supposed to be 3, negative 1/6, as opposed to getting the 0 over 0. All right, let's get rid of that. We don't need that. All right, we're also asked to find where the asymptotes are. So let's do that. So the vertical asymptote comes from the denominator. So x plus 3 equals 0, which means x equals negative 3. It's a real number, so the vertical asymptote is going to be at x equals negative 3. Now let's find the horizontal asymptote, or the end behavior asymptote. This function was an x minus 4 over x plus 3. That's first degree over first degree. It's improper but equal degree, so if you remember what we did with those, we take the 1x over 1x, or just the coefficients, 1 over 1, and that's going to tell me that the horizontal asymptote is y equals 1. Let's go ahead and sketch this. So when I sketch these, I always start by putting in the asymptotes first. So I'm going to put in my vertical and my horizontal asymptotes. Then I'll list out what points I know. I had an x-intercept at 4, 0, and I had a y-intercept at 0, negative 4/3. Now there's one other point that I know. That's the hole. Now the hole is not going to be a solid point. Instead, it's open because it's missing. So 3, negative 1/6 would be about here somewhere. And notice I used an open hole to show that it's a removed point. It's not actually part of the graph. All right, we have one vertical asymptote, and we have the hole. The one vertical asymptote means I'm going to have a piece of the graph on the left and a piece of the graph on the right. Can you see where they go? Take a moment. Well, on the left-hand side, to the left of x equals -3, it's either got to be above or below that vertical asymptote. But we know it has to be above because if it was below, it'd have to pass through the x-axis, and I don't have any x-intercepts over there. So the piece on the left is going to be like this. How about on the right-hand side? Again, I'm either above or below that horizontal asymptote, except that all my points that I got to go through are on the bottom. So this time, this piece of the graph goes from the asymptote approaching away to the hole, and then stops, there's a break, and then it goes from the hole and continues towards the other asymptote. This graph is discontinuous. It has both the vertical asymptote and the hole, so there's actually two breaks to this graph, which means when we write the domain, there's going to be two exclusions. The domain here is all numbers for x, except x cannot be -3, that's where the vertical asymptote is, and +3, because that's where the hole is. So when we write it, we're going to say the set of x such that x is not plus or minus 3. Now, if you use the interval notation, it would be from -infinity to -3, the union from -3 to the whole, which is 3, union, and then 3 to infinity. But it's a lot easier to use set builder notation with these. All right, here's another example. Let's take a look at this one. Here, we've got f of x equals x squared over x minus 1. Now, this thing will not factor out. It's already factored. So let's go ahead and start taking it apart, and let's find all of our intercepts, asymptotes, domain in the sketch. Here we go. So from the numerator, x squared equals 0, we can see that x equals 0. Now, this actually has multiplicity. It's actually x equals 0 and 0 again, but it's only one distinct x-intercept. But we're going to see that it bounces because of that multiplicity. Keep that in mind. That's going to come back later. Now, 0, 0 is also the y-intercept. I don't need to resolve it. Anytime I see 0, 0, I know it's both an x and a y-intercept. All right, let's go to the asymptotes. From the denominator, x minus 1 equals 0, which means x equals 1. We have a vertical asymptote where x equals 1. All right, let's talk horizontal asymptote. Here we have an x squared over an x. The higher degree is on top. This is improper, but bigger degree up top, which means this actually doesn't have a horizontal asymptote. Instead, it's got some other type of asymptote. Because it's an x squared over an x minus 1, we're going to have to divide this out. Given that it's just an x minus 1 in the denominator, we can actually use synthetic division. Now, you could also use long division, but the synthetic division is probably going to be quicker. So let me go and set this up with synthetic division. Now, it's kind of weird. It's just an x squared, which means when we set this up in synthetic division, it's going to be 1, 0, 0. 1x squared, no x's, no constants. The factor is x minus 1, so the solution down there was 1. All right, let's do our synthetic division. Bring down the 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is again 1. And 0 plus 1 is 1. So when we do this, we see that this thing is going to have a slant asymptote. And if you recall from previous lessons, we said that you can ignore the remainder here. So this is going to be y equals 1x plus 1. All right. Now this graph is discontinuous. We had a vertical asymptote. And the domain has only one exclusion. The only thing excluded out of the domain is the vertical asymptote. There's no holes in this one. So the set of x such that x is just not 1. All right, let's go ahead and sketch this. Let's put in our asymptotes first. So we have the vertical asymptote, x equals 1. We have a slanted asymptote, y equals x plus 1. That's going to have a positive slope, and it's going to start up at 0, 1. It'll look something like this. Put in the points we know. This time, the only point we know was 0, 0. Take a look at this graph. See if you can figure out where it goes. We have one vertical asymptote, no holes, which means this graph has two pieces. Piece to the left of the vertical asymptote, piece to the right. Can you figure out where they go? Well, let's start with the right-hand side. I think that's actually going to be easier. The right-hand side is either above the slanted asymptote, and it's going to be a little curve up there, or it's going to be to the bottom of that slanted asymptote, but there's no x-intercepts on the right-hand side, which means that first piece has got to be up top, trapped between the asymptotes. To the bottom, where would it go? Well, it's got to hug the asymptotes and go through that x-intercept. Now, keep in mind, I said earlier that that was a repeated x-intercept. It was a repeated multiplicity, which means it's going to bounce at 0, 0. So see if you can figure out how can it bounce off 0, 0 and still hug the asymptotes. It's going to look something like this. Now recall, when you approach that asymptote, if one side is heading down to negative infinity, that is as x approaches 1 from the left, the other side is going to approach it probably from the right, unless that denominator is the quantity squared. All right, let's do one more example. Why don't you pause the video at this point? I want to have you work this one out. Work this one out. If you're getting it all correct, once we resume the video and check it, then you're ready to start tonight's homework. If you're missing this, then you really want to watch those other videos that I've mentioned that are posted in Classroom and use those to get some extra practice. All right, so go ahead and pause the video, work this one out, and resume it when you're ready. I'll give you a moment. All right, hopefully I've had a chance to work this one out. Let's start by factoring to see if we have any common factors that we can say are wholes instead. So I'll factor it, and I get the f of x equals the quantity x minus 4 times the quantity x minus 1, all divided by the quantities x plus 2, x minus 2. There's no repeated factors, so there's no wholes here. Let's go to our x-intercepts. Here, the quantity x minus 4 times quantity x minus 1 equals 0, which means x is both 1 and 4. They're both real, so 2 x-intercepts. 4, 0, and 1, 0. From the denominator, let's finish our intercepts. Let's do f of 0 to find the y-intercept. If we substitute it in, I'm actually going to take the original equation. I think it's a little easier. And if I substitute in 0, 0 squared is 0. Negative 5 times 0 is 0. I'm left with just the constant of 4. In the denominator, plugging in 0, I'm left with the constant of negative 4. 4 over negative 4 is negative 1, which means my y-intercept is 0, negative 1. Now let's do the asymptotes. From the denominator, the vertical asymptotes are going to come from the solution of the quantity x plus 2 times quantity x minus 2 equals 0. There's going to be 2 vertical asymptotes. Now, we don't write it like this. Instead, those are the solutions, which means the vertical asymptotes are separate equations. X equals negative 2, x equals positive 2. All right, let's go to the horizontal asymptote. From the original problem, it was an x squared over x squared. It's improper, but equal degrees. We have second degree over second degree, so we look at those lead coefficients. A 1x squared over 1x squared gives me 1 over 1, which means my horizontal asymptote is again y equals 1. Now this graph had 2 vertical asymptotes. That means there's 2 numbers excluded from the domain. There were no wholes. So it's discontinuous, and the domain is a set of all real numbers, except x cannot be plus or minus 2. All right, let's go ahead and sketch this. I'll start by putting in my vertical asymptotes. There were 2 of them, and my 1 horizontal asymptote. 2 vertical asymptotes are going to give me 3 sections of the graph. Now let's plot the points we know. We knew that there was an x-intercept at 1, 0, and 4, 0. And we also knew the y-intercept is going to be 0, negative 1. All right, 3 pieces of the graph. Can we figure out where they go? Let's start with the left-hand side. On the left-hand side, there's no x-intercepts, which means that left-hand piece cannot be below the horizontal asymptote. Instead, it's trapped up top. How about the center? We're going to hug both asymptotes, both vertical asymptotes, and it can go through the center here because the horizontal asymptote's really only in behavior. So notice, we've got those 2 points, and it's got to hug the asymptotes. As x approached negative 2 from the left, it was going up to infinity, which means the other one's going to be coming up from negative infinity. So it's going to instead look like this. Now, what about the last piece? On the right-hand side, here we do have an x-intercept. So we've got to go through 4, 0 and still hug the asymptotes. If, as x approaches 2 from the left, was heading up to positive infinity, the right-hand side is going to be coming to negative infinity. So instead, it's going to look like that. There's your 3 pieces. All right, again, if you're still struggling with this and you need a little more help, make sure you look at the other videos posted under Math 3. All right, good luck.